what we showed, if the click problem has a polynomial time algorithm, then the independent set problem, vertex cover problem all have a polynomial time algorithm. Okay. So, remember P stands for the class of problems that are solvable by an algorithm in polynomial time. Okay. An algorithm for us is a deterministic Turing machine, if I want to define formally. And so, what we said, if you have a polynomial time algorithm for click, I can use that as a black box to solve independent set. How did we do that? We take, in a graph where I am interested in finding maximum independent set, I take its complement, give it to the click black box algorithm, and from there I can get this. Similarly, if I find maximum independent set in a graph, I also know immediately minimum vertex cover. It is a complement of that set. And towards the end, I said something which we will prove today, that not just vertex cover independent set, which are sort of graph problems, but even SAT, which is a problem in logic, also has a polynomial time algorithm. We will see how that is true today. And I also defined this class of problems called NP. Again, we defined it as decision problems whose S answer has a polynomial length certificate. I am going to say short proof that can be verified in polynomial time. Okay. So, again the formal definition is through non-deterministic Turing machines, and we observe that so everything in P is in NP, okay, and the converse is open and has $1 million price for it. Okay. So, NP does not stand for not polynomial time, okay, non-deterministic polynomial time. So, I have seen people typically saying, oh, this problem is an NP, and what they mean is it is a hard problem. That is not true, right, because we have seen the entire P is actually sitting in NP. So, NP also contains problems that are solvable in polynomial time. So, do not mistake NP as hard problems. Okay. NP is all about verification. Okay. So, now we will do this and then connect to how all these have anything to do with that converse open problem. Okay. So, that is sort of the plan for the first lecture. So, let us try and do this. So, now, so what do I, so I want to show this, right. So, what is given to me and what do I have to show? Yeah. So, what is given?
Max
Click is a key. So, I have a black box algorithm which you give a graph, it gives you the max click. it gives you max click size or max click, whatever they are actually. So, let us say max click size it gives. I want to use that as a black box to design a polynomial time algorithm for SAT. Okay. So, what is my input to a SAT? A Boolean formula. Okay. So, n variables and a bunch of clauses, and I want to design an algorithm for SAT. I do not want to design it from scratch, because that is again a hard problem, but I want to use this black box to solve that. Okay. Something to keep in mind. So, what do I have to do then? I take the SAT instance and what do I have to do? Reduce. So, what does that mean? What do I have to do? Create what? A graph. I have a Boolean variables and clauses. Somehow I want to create a graph in such a way that the max click solution in this graph gives me the answer to my question, is there a satisfying assignment or not. Okay. Keep that goal in mind. Always do not get bogged down by the actual proof. Before that, have a big picture in your mind. What do I have? What is given? What do I have to do? And then you get into the proofs, right. So, I have a black box algorithm. Let us call this MCQ, which takes a graph G and gives me max click size, let us say. And I have a formula which looks like this. And each CI is looking like some y1 or y2, or let's even make life simpler and say I am going to prove this for 3 SAT, which means that a formula where every clause has exactly 3 variables. Okay. So, maybe it will be y I1, y I2, y I3, and where each y I j is some x I or some x k or x k bar. Okay. My variables are x1, x2, xn, that is my formula. So, I have given some arbitrary formula looking like this, where it has m clauses and n variables, and each clause is an OR of 3 literals, and a literal is a variable or its negation. Okay. From here, our goal is to construct a graph to maintain this property that the graph has a certain click size, if and only if this formula is satisfiable. Okay. Okay. And often people make this mistake of, let me take this formula, if it is satisfiable, I will construct this graph. No, you do not know any such thing, right. You cannot go and check whether it is from the instance. I have to construct this graph to maintain this property. Okay. Fine. So, the graph I am going to construct is, so I am going to construct this graph G. It looks like this. For each clause, I am going to have 3 vertices, one representing. Okay, so, this will have each vertex represents an occurrence of a literal in the clause. Okay. So, the class first class contains x1 or x5 or x3 bar. I will have the 3 vertices here, which is going to represent. So, suppose C1 is x1 or x5 or x3 bar. I will have 3 vertices and denote them some sort of a label to indicate that it corresponds to x1, x5, x3 bar. Okay. And I do that for each of the m clauses. Okay. So, this graph, how many vertices does it have? 3m. Okay. Now, I am going to define the edges of the graph. Okay. So, I am constructing a graph from the formula and I am going to construct edges of the graph. For now, let us say I construct all edges between these parts. Okay. So, E is all edges and no edge within each set. So, E is going to be V W, where V is in some C I and W is in some C J, I not equal to J. Okay. Now, that is all my graph for now. Okay. I will change it later. What is the max click in this graph? What is the size of the max click? Remember, click is a subset of vertices which are mutually adjacent. Okay. So, this graph has no edges inside and I am adding all edges across. Okay. Between any pair of the CIs, I am adding all edges. So, how big a click can you have? M. Does everyone see that? Can you give me some M click? I mean, pick a vertex here, pick a vertex here, pick a vertex here, pick a vertex here, they are all mutually adjacent. So, that is a click of M vertices. Is there a possibility of a larger click? Can I get a click on M plus 1 vertices? Why not? Why? Why not from 2 from one set? Because we constructed this graph and we added no edge between any pair of vertices inside a set. So, you cannot have a click of size m plus 1 because or even more, because such a click must necessarily pick at least 2 vertices from each set, some set, and I made it sure that there are no edges within each set. So, the maximum click it can have is m. Okay. So, now what do I want? I want the property that my formula f, this is my formula f, is satisfiable, means that there is some assignment that sets every clause to true if and only if there exists an m click in G. This is the kind of thing I want. Okay. I mean, it is not true at this point, you will see why, but I want this property. Why? Because what is our problem? I want to know whether the formula is satisfiable, right. That is a satisfiability problem. Given this Boolean formula, can I set each of the variables to 0 or 1, so that all clauses are simultaneously satisfied? That is my problem, and I am going to construct this graph and I give it to my this algorithm and say, tell me what is the max click size in this graph. If it happens to be m, I want to conclude that f is satisfiable, and if it is not m, if anything less, I want to conclude f is not satisfiable. Obviously, this is not true at this point, right? Why? I want this to happen, but I am saying no, I need this graph is not a good enough graph, I need to modify it a little bit. Why? What do you mean? I defined that. I gave you the graph. It's correct. We don't know. M click exists regardless of what the formula is, right? So, even if the formula is not satisfied, M click will exist. So, so this is not a nice enough graph for me to capture the formula instance, because if whether or not f is satisfiable, this graph has an m click. Okay. So, it is not good enough, I am going to modify it. Okay. Now, let us come back, how am I planning to prove that, and then we will see where the proof fails, and then we will see how to fix this graph. Is the plan clear? Okay. I am just sort of the way you will see it is that somebody gives a formula and you will get a graph and we will prove it. I am trying to argue how you would even construct the graph by giving a wrong graph and see where it fails, then it tells you how to construct the graph. Okay, good. So, what is my intuition of how would I prove this? Well, suppose, so I want to, it is an if and only if statement. I hope you know what that means, that I need to do both directions. So, suppose f is satisfiable, my formula has C 1, C 2, C m, right. So, that means there is some assignment to the xi's which will make C 1 true, which will make C 2 true, C 3 true, C m, all of them simultaneously true. So, let us pick that assignment. Suppose f is satisfiable, I am trying to do the forward direction, and I have somebody from each of the clauses satisfying that clause. So, maybe this, whatever that variable satisfied C 1, this satisfied C 2, this satisfied C 3, maybe this satisfied C m. Okay. There is some assignment to the xi's by which each of the Ci's is satisfied. I want to go ahead and pick those corresponding vertices here and argue that they will form a clique there. Okay. I mean, the way I have drawn any set of m vertices will form a clique anyway. So, this direction will not give you too much intuition to what I am trying to say, but let us look at the backward direction. Okay. Suppose G has an m clique. That clique you all observed that must necessarily pick exactly one from each of these parts, right, because I can't make up m by omitting a clause. I can't pick 2 from any clause because it won't be a clique. So, it must pick something from here, something from here, something from here, something from here. Now, I want to get back a satisfying assignment to the variables. What I am going to tell you is that, oh, set that variable to true, set this variable to true, set this variable to true, set this variable to true. That is an assignment that will satisfy all the clauses, but it breaks down. Where does it break down? There is a problem.
Complement also can be given.
Exactly. So, where is the problem here?
X is true and X complement also true.
Very nice. So, the clique I obtained, for example, suppose contains x 5 here and contains x 5 bar here. And I am going to say, hey, from the clique I am going to obtain my original satisfying assignment. How am I going to do? Set x 5 to true, set x 3 bar to true, set x 5 bar to true. I mean, you have to tell me, make up your mind. Do I want to give x 5 to true or false, right? I cannot give both x 5 and x 5 bar to true. There is a problem there. So, the way now I am going to go back and draw my graph, I want to make sure that these guys are not edges. They don't, so that when I have a clique here, I do not have a problem of some xi here and xi bar here. Okay. So, now I am going to redo this graph here, right. Keep in mind this graph is not something I am constructing based on whether it is true or whether it is satisfied or not. This graph is something I am trying to get intuition from what I am trying to prove. I am sort of reverse engineering my graph. Okay. So, this is very important. Do not assume that this is satisfied and taking the assignment and constructing the graph. Graph, the moment you give me the formula, I am going to construct the graph. The graph is now going to have these 3m vertices and all edges of the form like this, except V is equal to W bar, okay, because V corresponds to some literal. Okay, I am overusing the symbols here. V is from here and W is from here, and I am going to draw an edge except when this is the negation of that, then do not draw an edge, otherwise draw an edge. Okay. This is my graph. I do not know by doing this reverse engineering I confused you more or helped you understand, but now let me start all over again. You are given a formula like this, a 3 sat formula with clauses. I will construct this graph where each clause has 3 vertices, each vertex corresponds to an occurrence of a literal in Ci, and I draw an edge between any pair of vertices, one from each this clause, one from the other clause, as long as one is not a negation of the other. I have done that. Now, let us try and prove this. So, now I may not have an M click in this graph all the time. Okay. This is now important. I mean, earlier there was always an M click, because pick any one from here, 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 they are mutually adjacent. Now, it may not be, because I have prohibited some edges. Okay. So, now if f is satisfiable, I will do the same thing, pick whatever variable that sets this guys to true, set this to true, and so on, and they will form a clique, because it is not possible that you have an xi here and xi bar here, where these variables are chosen to satisfy the formula. So, they will form a clique. Conversely, if you have a clique, you must pick one from each of these, and these guys cannot be negation of each other, because I did not have, because they form a clique, and so they would correspond to a satisfying assignment. Okay. Good. So, this is somewhat surprising in the sense that, SAT is not a graph problem, it is some problem in logic, and we managed to somehow reduce is not the word I used so far, but though I have been talking about it, we reduced it to SAT in a way that it is an equivalent instance. In the equivalent instance, somehow it encodes satisfying assignments. Whenever you are satisfying formulas, whenever this is satisfied, there is an M click, and whenever there is an M click, it is satisfied. Okay. So, now I can go back and say, okay, take the formula, construct the graph, give it to this max click algorithm. If it comes back and says yes, the max click size is M, I know my formula is satisfied, and if it says click size is less than M, I know my formula is not satisfied. Good. So, this all of this is nice. Now, what happened in 1971, Stephen Cook and Leonard Levin independently showed something like the following, that if SAT, okay, by the way, this whole thing works for, I mean, where did I use the fact that it is 3 SAT? I did not really use the fact. I mean, only where I used is because it is the number of vertices is 3 m, but if it is otherwise much larger, it is okay. Number of vertices is still polynomial in the input size, and you can do this click algorithm and get your answer. Okay. So, what Cook and Levin showed is that if SAT is in P, then some very powerful statement is true. Every problem in NP is in P. Okay. So, what we showed here, we actually gave proofs here. If click has a polynomial time algorithm, then independent set, vertex cover, SAT, they all have polynomial time algorithms. Okay. But Cook and Levin, this is a very celebrated theorem. In fact, they all won Turing Award for this result. The Nobel Prize in Computing is actually called Turing Award, and these people, among many others, are, I mean, Richard Karp proved some of these results, and he also won Turing Award. So, what Cook and Levin showed, so somehow we are reducing click to independent set, click to vertex cover, click to SAT, but Cook and Levin said does not matter. I am reducing SAT to every problem in NP. So, SAT is somehow so powerful, so hard that if it has a polynomial time algorithm, then the entire this question is resolved. Okay. And it is a important theorem, and the way they showed, I mean, see, it is mind boggling how you would show something like this, because to show that every problem in NP has a polynomial time algorithm, I mean, it is hard enough to show that if click has a polynomial time algorithm, SAT has a polynomial time. We reduced click to SAT, but now we want to reduce SAT to an arbitrary problem in NP. We do not even understand that problem. Here at least we understand how the click is, how SAT is, and so on, right. So, the way they showed is by using the formal definition of what NP is, the Turing machine definition. So, basically took SAT, modeled it as some sort of a Turing computation, that if you take a non-deterministic polynomial time algorithm, it has a certain behavior, certain Turing machine, there is a computation, and they modeled the whole thing using SAT, a Boolean formula, in a way that this formula is satisfiable if and only if this computation stops in polynomial time and answers yes. Okay. But yeah, so for our purpose, this proof, we teach it in our PhD level courses, advanced students learn it, but it's okay if you understand it as a black box. And now because of this, notice that click also has such a behavior. Tell me why. So, if click has a polynomial time algorithm, every problem in NP has a polynomial time algorithm. Why? Because of this transitivity of this reduction. Because we know if click has a polynomial time algorithm, SAT has a polynomial time algorithm, but if SAT has a polynomial time algorithm, NP is contained in P. Similarly, about independent set, vertex cover. So, now you have this whole set of problems. So, let us just call these problems as NP hard. Okay. It is just a definition, right. Somehow they capture hard problems in NP. Okay. So, this picture of NP is here, P is sitting inside, and we do not know whether anything is here at all, right, because that is a question here, and NP hard somehow are problems here. And now after Cook, Levin showed 1972, Richard Karp came, and by the way, the result at that time was not stated like this. They showed, their paper was titled "The Complexity of Theorem Proving Procedures" or something like that. Even the term NPP was not there at that time. Okay, and this is all defined later. And the year after that, Richard Karp came up with these kind of reductions. He came up with some 21 problems, and he said, that if these problems have a polynomial time algorithm, then everything in NP contained in P. And the way they showed, I mean, Cook did the hard work of reducing arbitrary NP problem to SAT. Now, to show something is NP hard, you just have to pick one of the NP hard problems. Could be SAT, could be independent set, could be vertex cover, and reduce to your problem in polynomial time. Okay. Something I did not pay too much attention to, but the whole reduction took polynomial time, because polynomial in the input size. Okay. So, that is how the whole theory of NP hardness or NP completeness was born. So, what is NP complete problems? Are NP hard and also belong to NP. They are also in NP. So, it is NP complete. Again, do not worry too much about the difference between these two things, and I know I get asked this difference, what is the big difference? I don't want to get too much into it. Okay, so so it is believed now that there are thousands of problems which are NP hard. With this, what does NP hard means? Essentially, it means this: if that problem is NP, then every problem in NP can be solved in polynomial time. And since NP is all about verification, P is about solving, it's believed that these two are conceptually different, computationally their complexities are different, and so unless P is equal to NP, NP hard problems do not have polynomial time algorithms. Right? Do you see why? I am rephrasing whatever, because if an NP hard problem has a polynomial time algorithm, what happens? P equal to NP, because NP would be contained in P. That is the definition of NP hard, the way we called it. And since we do not expect P and NP to be the same, so I mean this is not proved, there is no, it is still an open problem. We do not believe that they have polynomial time algorithms. Okay. Now, let us recall where we started off, right. We were trying to show lower bounds for problems. We wanted to show that our problem cannot be solved in certain time, right. That is what we started off. We said max cannot be done better than linear time. You cannot have an algorithm to find the maximum of numbers in log n time. You cannot sort in better than n log n time. These are the kind of lower bounds we saw. In between, we had this problem, matrix multiplication, matrix inverse, where I do not have a clean lower bound. There is a difference between upper bound and lower bound. We can do it with n power 2.23 kind of a running time for matrix multiplication inverse, but we do not know whether that is best. Okay. Then we moved on to this kind of problems, click independent set, where some of the best algorithms we came up with was something like 1.4 power n exponential time. Now, if you show that it is a NP hard, then you somehow give some evidence that you do not, that any algorithm to solve this problem need more than polynomial time. Okay. In this case, it is not a theorem, but it is an evidence, because it is under the belief that P is not equal to NP. Okay. So, let us do one more reduction for you to get the hang of how you show NP complete reductions, and then I want to move on to something else. Okay. So, any questions or any comments? Right. So, based on whatever we did and this statement, what we now know is that vertex cover, independent set, click, SAT, all of these are NP hard. We do not expect a polynomial time algorithm. Okay. Now, let us do one more reduction, one more problem. Again a fairly and that is a set cover problem. Okay. So, what is the problem? Your input has a universe U, let us call it 1 2 up to n, and then there is an F which is a family of subsets of U. Okay. So, F contains some F1, F2, some Fm, each is a subset of 1 to n. And the question we want to ask, okay, by the way, so I should make one remark here. We said the whole notion of NP is defined for decision problems, problems for which the answer is yes or no. Though here I kept talking about max click, min vertex cover, max independent set and so on. Those are not decision problems. Those are sort of optimization problems. So, how can I convert them into a decision problem?
Is the max click n cells?
Yeah, sort of, but instead of asking is the max click k size, I'll tell you why the problem there is. I would ask, is there a click of size k? Okay, but how does that solve the max click problem? You repeatedly ask, right? So, is the click size, is there a click of size k in the graph? And if the answer is no, then go down and check for k minus 1, k minus 2 and so on, because when you are talking about maximization problem. If you are talking about minimization problem, start with is there a vertex cover of size 1, 2, 3 and go on. So, you can ask this n times. So, in some sense you do not lose too much generality by restricting to decision problems. Okay. So, again let me phrase this as a decision problem now here, that is why I came here. And so, your input also has some integer k. The question we want is that does there exist an f prime let me write and we will see an example. Okay. Many of you are mathematics students, so it's okay to write this so mathematically. So, what I am asking, is there a subfamily? Can you pick some k sets from here? There are totally m sets, out of which now k is some integer. Can you pick some k sets from here, f prime is of size k, that when you do the union of the sets, they should cover the universe. Okay. So, that is a problem. Okay. Ideally, it is a optimization problem. So, minimization or maximization? Minimization. I want to pick minimum number of sets from here that would cover my universe. Okay. So, let us see an example. Say u is some 1, 2, 3, 4, 5, 6, 7, 8. My family may contain 1, 7, 8, 2, 6, 8, 1, 2, 3, 4. And so, I want to know what is the minimum number of sets you can pick from this family that would together cover my universe. How many sets do you need? 3 sets, right. So, I can pick this last 3 sets, there may be other combinations, I do not know. So, that is the problem. So, is it in NP? Okay. Yeah. So, I have fixed an integer k. So, how do you show it as an NP? Yes. So, what do you give me as a proof? Remember the definition, there is a proof, short proof, a polynomial length proof, and I can verify in polynomial time. So, what proof? So, if the answer is yes, the S answer, I do not care about no answer, okay. That is a different ball game. So, suppose k is 3 and I ask or 2. k is 3, let us say 2, for 2 it is no anyway. So, 3, can you give me 3 sets that will cover the entire universe, and suppose the answer is yes, how would you prove it to me? Well, you did prove it to me for this example, right. You gave me 3 sets, that is a proof. And how do I verify? I take the union, I first make sure that those 3 sets are actually in the family, take the union and check whether it is covers everything, right. So, this is about verification, but if I actually want to solve it, it is hard. I mean, what would be a brute force kind of an algorithm? All possible what? What combination? For brute force, you can always say all possible combination, that is a standard answer, but what is the combination?
Start with like one subset at a time,
Mm-hmm.
see
Okay.
how much it covers, and
Right.
then like subsequently add subsets one at a time and see if it covers the set in every step.
Yeah. So, try all 1 element subsets, try 2 element subsets, try 3 element subsets of, I mean, when I say subset, by the way, 3 element subset of this family, which means 3 sets, 2 sets. So, try so many, and or if I care about k, you can try all possible sub families of size k and check whether they cover that. So, that is going to be how much time? This is also a standard answer you can give, or in fact, that is not. If I am trying all possible sub families of size k, m choose k, right. M is the number of sets here, I pick some k of them, okay, and for each one of them I have to do some more time to check whether they cover. So, this is exponential in k, right. If in particular, if I want to find the minimum, it is going to take 2 power m, because I may want to check all possible subsets and so on. Okay, so, before we even try and show its NP complete reduction and all that, understand more about the problem, right. Is it an NP? Is there some algorithm you can come up with? Why is it an exponential algorithm? Okay, can you think of a greedy algorithm here? Right, what you should connect to some problem now that we have already seen, because what are we trying to do? We want to pick some subsets to cover our universe. So, what is a natural set to pick? Pick a set which has the largest number of elements, add it to your solution, and then and some things are already covered, and then out of the remaining pick a set that picks the largest number, keep doing. So, first thing you have to check is why is this algorithm not correct, right. It may not give you optimum all the time. Why do we believe so? Because I am going to show it as a hard problem. Okay, I am going to show it is an NP hard problem. So, we do not expect such an efficient algorithm to work all the time. Okay. So, first we have to try all these things. I am just saying the moment some problem is introduced, try for some brute force algorithm, some greedy algorithm, why does it not work and all that, and understand it. And then now I am going to show, no, not me, you are going to show that this is an NP hard problem. It is an NP, we have already seen, right. You give me some subfamily, I just have to do a union and verify. But now I want to show that it is hard. How do I show?
Find another NP problem.
Find a
Another NP hard problem.
very good. Find another NP hard problem and reduce that problem to this, because we want to somehow argue something like, if set cover has a polynomial time algorithm, then it can be used as a black box to solve some other problem which we already showed hard, right. So, that is how you show that this is also hard. So, what is the some other problem we want to think about, right. First thing is always hard, you do not know, because there are hundreds of problems now which are NP hard. So, where do I start from is never easy, okay. And then the second step is to do the actual reduction, okay. But right now I have given you a glossary of 3-4 problems. So, your job is not that hard. You can, what problem would you want to reduce from?
Sand.
Look at this. Which problem looks like a covering problem?
Vertex.
Vertex cover, right? So, first thing is, this is how you do relations. This is how you relate, right? Vertex cover, vertices are covering edges, and set cover, your sets are covering the universe. Okay. So, let us start from vertex cover. And the general philosophy, if something is not obvious, you can start from SAT. And yeah. Okay. So, here I am going to start from vertex cover, and I want to reduce to set cover. Okay. So, we are going to design an algorithm for vertex cover, that is how you should keep in mind, using a black box algorithm for set cover to argue that set cover is hard. Okay. So, what is the input for vertex cover? Graph, right. So, I am given a graph, and let us also assume that there is an integer given, because it is a decision version of the vertex cover problem. I am not looking at minimum vertex cover, I am asking, are there k vertices that will cover all edges. Okay. So, now I want to convert this into an instance of set cover, which means I need to create a universe and a family of subsets. So, what should be the universe? All the vertices of the graph.
Edges.
Edges of the graph. Okay. Edges. Okay. Why do you say edges?
In vertex cover, we cover edges.
Exactly. That is all. What are we trying to cover? Edges. Here, what are we trying to cover? The universe. So, the universe should be edges. Okay. Now, I have to give you a family, right, and anything in the family is a subset of the universe. So, it is a subset of edges, right, because these are subsets of the universe. So, I have a graph G and you are given k. I want to pick k vertices to cover all edges. So, now my universe is edges. I need to pick some k. It need not be k, it could be some k prime you can come up with. So, that k prime subsets cover edges correspond to some k vertices covering the edges. Okay. So, what should a typical set here should be? And how many sets should there be? How many sets should I have? Because again, let us keep this kind of a goal. Earlier we said f is satisfiable if and only if there is an m click. Here the similar kind of a goal, what I want is that G has a k sized vertex cover if and only if this u comma f has k or k prime, I do not know, sized set cover. So, I want this kind of a correspondence between the graph and the family I am constructing, right. So, how many sets should I have and what should each set have? So, we said each set is a subset of edges. Okay. So, how many sets should I have? One set
Each edge.
corresponding to each edge. Remember, this k corresponds to what?
Number of
Vertices I pick in the solution, right? So, I am picking k vertices in the solution, and if I want that kind of a correspondence, I should be able to pick k sets here. So, each set should correspond to a vertex. Each set should correspond to a vertex, and what do I have in the set? Okay, so I'm going to say f1, f2, fn, and what should be the ith set?
Instant edges.
On
vertex.
vertex I, right? That's it. So look at all edges incident on vertex I. We're done. That's it, right? Now you need, we are done, meaning you need to complete the proof of this. But it should be fairly obvious now, because you've sort of constructed your instance to satisfy that. So you should be able to now do that, right? Let's go through the proof. So if G has a vertex cover of size k, what does that mean? There are some k vertices that cover all edges, right? Now I have to show, in that case, there are some k sets that will cover my universe, which is all edges. What are the k sets you will pick? What are the k sets you are going to pick? So there are k vertices that cover all edges of the graph. I want to argue that in this family there are some k sets that will cover my universe. What k set should I pick?
Incident to the k vertices.
Yeah, the sets would correspond to vertex. So there is a set corresponding to this vertex here. There is a set corresponding to that vertex here. So pick the corresponding set, the set corresponding to each of the vertices. There are k of them, and those k edges will cover the universe, because that's the definition of k vertices covering all edges mean. And the converse is, symmetric, pretty straightforward, because if you have k sets that cover all edges, then go and pick the corresponding k vertices that will cover all the edges, right. So, this is, set cover is actually something more general that captures a lot of other kind of covering problems. Okay. So, this is how you show, right. So, often some of the constructions are really magical, but you have a goal like this in mind. So, you are trying to encode this problem into this problem. Okay. Good. Okay. So, now we have this kind of reductions, hundreds, thousands of reductions now, that there is this big list of NP hard problems, and they are believed not to be in P because there are lots of them, and if any one of them has a polynomial time algorithm, all of them have a polynomial time algorithm. So, trying to show a problem is NP hard is an evidence to show that it cannot have a polynomial time algorithm. Okay. Okay. So, now I am going to switch gear and talk a little bit about something else, which I will continue in the afternoon. But before I do that, any questions on this so far? Because this is one of the common thing in the form we asked, what is it you want to know, and several people wrote, we want to understand more about NP completeness. So, hopefully your prayers were answered or we can always pick it up more in the discussion time. So, now there are two questions I want to toss it to you, and then we will come back and pick this up in the afternoon. Okay. So one question is, okay, so I have this huge, NP complete problems, let's say SAT, vertex cover, independent set, click, maybe even 3 SAT, general SAT, and we know that unlikely to have polytime algorithm. Okay. Now, I mean, these problems don't go away. They are important practical problems, and unfortunately, there are no efficient. Okay, I mean, you would have seen a lot more, right? TSP, traveling salesperson problem, Hamiltonian circuit, and so on and so forth. So they need to be solved somehow because they are important, but unfortunately, in theory, you cannot have an efficient algorithm to solve it. So, how do we deal with it? There are various approaches to deal with it. Okay, I am not going to talk about it, but each one is a course by itself. So, there is approximation algorithms. So, as I said, even though we phrase it in decision problem and this whole theory is about decision problems, our real interest is optimization problems. So, now if I say, okay, finding minimum vertex cover is hard, finding maximum independent set is hard, maximum click is hard, but maybe I do not want the real optimum, give me something close to optimum, right. That is what approximation algorithms talk about. But I want to spend only polynomial time because I know that is what correspond to feasible time. So, I want to solve in polynomial time and you are telling me that I can't get exact algorithms. So, can you give me something approximate, right, something close to. So, this is a huge area, right. There is also an empirical, lot of engineering problems are NP hard and they will do some simulations, various heuristics and come back with it. But in theory, we care about measuring the quality of the algorithms. It is not enough to say, okay, I have this algorithm for vertex cover, it may not give you minimum vertex cover, but it gives you close to it. I mean, how do you know it is close to it when I do not even know what the optimum is, because optimum is so hard to find and you are telling me it is close to optimum, will it be close to optimum. So, here the real question is measuring the approximation ratio is a challenge, right. What is the ratio of the solution produced compared to the optimum? The running time is not so much of a concern as long as it is polynomial time, but can I get close to approximation? This is a whole new area. There will be like 3 or 4 or 5 books on this, one can do a whole course on it. Okay. And then okay, a problem is NP complete means that you do not expect a polynomial time algorithm for all inputs, but suppose I know something about the input, can I do something better? Okay. So, let me ask you this trivial question, right. Okay, click problem is hard, finding the max click is hard, we do not expect an efficient algorithm, that is what we have seen by doing these reductions. But suppose I tell you my graph is a bipartite graph. You know what a bipartite graph is? Many of you are graph theorists. You know what is a bipartite graph? Somebody tell me.
Vertices.
Such that
Each vertex.
so that you can partition the vertex set into 2 such that there are no edges inside each part. The edges are going only across. What is a nice characterization for bipartite graphs?
Can have no cycles.
Same thing. Huh?
No odd
There are no
cycles.
odd cycles in the graph. There are no cycles with odd length. So, now suppose I tell you my graph is bipartite, I want to find the maximum click in the graph.
It will be even.
Yep. No, this one. How do you find the maximum click in the bipartite?
Even.
Hmm? Your maximum achievement.
size.
Yeah.
My age.
2, sir.
We
Two,
can.
sir.
Anybody?
2.
Why?
If 3 vertices we take, any 2 does not have an edge.
Yes, because you don't even have a triangle in the graph. How can you have any big click? So you can only have, in fact, even 2 may not be there. It can be 1. Right? When do you have one click? When is the max click 1? When there are no edges in the graph. Then the max click. So okay, so that's sort of an extreme example where if I know something about the graph, then the problem is not NP hard. You can solve it. So that's what the special instances are. Suppose the graph is a planar graph, chordal graph. There are some big industry of graphs. This again there are books on it. Perfect graph, chordal graph, comparability graph. So one can study some real world instances which have some special properties, and then you can talk about efficient algorithms for such instances, if not for the all instances, because you don't expect it for all instances. Okay. The other problem I would little bit touch upon next lecture is that, see, let us say for vertex cover we saw a good algorithm, not polynomial time, but some exponential time algorithm, right. Do you remember how we did? We saw some, I mean, when I started off yesterday with vertex cover, we started off with some branching algorithms. Excluding and including a vertex. Through that process, we said take the highest degree, include it or exclude it, and we had a recurrence relation, solved it, and I think I gave you something like a 1.4 power n kind of an algorithm, right. And pretty much such algorithms will work for independent set click by just doing the complement and doing the same thing. So, but unfortunately for SAT, nothing better than two power n is known. The general SAT, 3 SAT you can do much better, but so which means what am I saying here? Even here in this class of problems, while they are all NP complete, we do not expect a polynomial time algorithm, but in the exponential world also there are differences, right. Some have a 1.4 power n algorithm. In fact, what I showed you was 1.4 n, but it has been improved a lot to 1.2, 1.1 kind of an n, whereas something like SAT, also NP complete, has nothing better than 2 power n. Hamiltonian cycle or TSP, for example, what would be a brute force algorithm, if you know what a Hamiltonian cycle problem is? All is true. I want to know the complexity. Okay, let us understand what is a Hamiltonian cycle problem. Given a graph, does it have a cycle that visits every vertex exactly once, right? This is a problem, and it is related to traveling salesperson problem. That is a more general version of Hamiltonian cycle problem, and these are all NP complete, no polynomial time algorithm. But what is a brute force algorithm for Hamiltonian cycle?
Find all cycles and check if it's Hamiltonian.
Okay, how many cycles are there?
Cycles in 10 minutes.
So how? So no, first of all, I want a cycle that visits every vertex, right? So I will say, okay, try 1, 2, 3, 4, 5, 6, 7, 8, n, and see whether that's a cycle. Okay, no, it does not, because maybe there is no 3, 4 edge is not there. Okay, I move on. Try, what am I trying? Trying all permutations. Try all because any cycle, if you read out the vertices, that's visiting 1 to n in some order. It's a permutation. So one brute force algorithm is try all permutations of 1 to n and check every consecutive thing is actually an edge in the graph, right. So that will tell you whether you have a Hamiltonian cycle. It's again a brute force algorithm. How much time will that take? How many permutations are there? n factorial. Okay. So, it is even worse than 2 power n. Okay. So, a brute force algorithm here is n factorial, but strictly speaking n minus 1 factorial, because 1 2 3 4 n 1 and 2 3 4 n 1 2 are all the same. So, you can divide by n. But the point I am trying to say is that, yeah, they do not have polynomial time algorithm, or you do not expect to have, because they are NP complete, but they have all kinds of different kinds of complexities even on the exponential time. There is one has n factorial, one has 2 power n, one has 1.1 power n. So, you can talk about good exponential time algorithm. Okay. So, I know, live with the fact that it is an NPR problem, so you have to design exponential time algorithm, but can you be more clever in designing exponential time algorithms, improve the base of the exponent. So, these are all directions and areas coming out of the PNP question, and each is a full blown, there are about 20-year-old research on each of these topics, maybe even more in some of them. There are books on this, and so I just want to throw that there are a lot of directions in algorithms to explore. Okay. So, let me now tell you the story where we started off, where we were, right, and then I will do some connections in the afternoon. Okay, before that, may I talk about one other problem. Let us talk about computing the diameter of a graph. Okay. So, you are given a graph GVE, undirected graph. What is the diameter? It is max distance x y over all x y and b, but d is the length of the shortest path from x to y. Okay. Let us see, can you give me some brute force algorithm for it. So, is the problem clear? Given some arbitrary graph and unweighted, undirected, unweighted, what you want to find is, what is the largest distance in this graph. Okay. So, any ideas?
LC2.
LC2 pair, but how do I know the distance?
Extra.
The extra,
You're applying it every vertex and
the extra is an overkill. Yeah, you can do the extra, but the extra you use it for if there are weights on the edges. Here it's unweighted. So, BFS, breadth first serve. So, let's go over the algorithm. So, what do you do? So, what do you do? BFS requires a starting vertex. Let's think of some simple brute force.
need for all the vertices.
Hmm?
Need for all the
Run what for all the vertices?
BFS.
Exactly. Okay, good. Right. So, I start from a vertex, I do a BFS. What do I get at the end of it?
Distance.
Farthest vertex.
Distance.
Farthest vertex.
No, if I do a BFS in general starting at x, some vertex, what do I get?
Shortest path between every.
Shortest path,
Between the starting vertex and every.
exactly. That's what you get. It's sort of like what you get in Dijkstra, the single source, but here there are no weights on the edges, so you don't need Dijkstra. You can just do a BFS. So, do a BFS V for all V in V. So, when I do that, I start at V and I have this whole tree, and I know the distance from V to every, the shortest path. That, I mean, we are using the property of BFS, that BFS actually finds the shortest paths. So, we know the length of the shortest path from V to every other vertex, right. Now, do this for every V, you got all pairs shortest paths, and among them you pick the largest. Okay. How much time does BFS take? M plus n, if there are m edges and n vertices, and you are doing it n times. So, that is n times m plus. Okay. So, if you know, so we will ask the question we have been asking, can you do better, right. So, even if m is, if the graph is sparse, there are not too many edges, suppose there are only order n edges, then this becomes n square, right. Can I improve n square is the question we want to ask. Okay, is there an algorithm better than n square to find the diameter of an undirected graph, undirected sparse graph? That is one question, and we are going to relate that to, can we do SAT in better than 2 power n? Okay. So, this is nice. So, let us again, I was going to tell you the story we had. Initially, first lecture I had a bunch of problems, max, min and max sorting, where we know tight upper and lower bounds, right. Sorting as an upper bound of n log n, lower bound of n log n, such tight, if you care only about the asymptotics. That is one set of problems we saw. In between, we saw something like matrix multiplication inverse, where there is some upper bound, some lower bound, there is a gap, and I would put diameter also in that set, right. They are polynomial time solvable problems, but we do not know the limit, we do not know, is there a better algorithm question, we do not know. And then we move down to NP hard problems. The fact that they are NP hard means that you know that you do not expect a polynomial time algorithm, that is all. Now, I am going to say, okay, assuming P not equal to NP, those problems do not have a polynomial time algorithm. Now, I am going to say, assuming SAT cannot be solved better than 2 power n, I will argue that diameter cannot be done better than n square. Okay. So, it is very nice, it is not an NP complete kind of a reduction, right, it is a different kind of reduction. This is fairly a recent work, in the last 10 years this thing has picked up. So, I will tell you more about it in the afternoon, connecting polynomial time solvable problems and exponential time problems and see how they are related, and using some assumption, that is also an assumption, just like P not equal to NP an assumption, we are going to make some other assumption that SAT cannot be solved in better than 2 power n is an assumption. It seems so, because people have tried hard, there is no good algorithm. Under that assumption, we can prove a lot of other interesting lower bound results. Okay. We will see that in the afternoon.